Well, everybody, hope you're doing well. This is our introduction to geology, and we're going to get right into it and discuss our first topic, minerals. So far you've kind of looked at the four branches of our science: meteorology, astronomy, oceanography, and geology. Of course, geology is the study of the earth, the solid portions, the surface, and the interior, the liquid portions. So some of the topics that we're going to cover throughout the course in geology, which is kind of where we'll start out, is minerals and rocks. We'll move into geologic time with the rock record and how the provinces of Virginia formed. We'll then move into dynamic Earth, which is earthquakes, volcanoes, plate tectonics, weathering and erosion. We'll get into in geomorphology, glaciers, rivers, streams, wind, waves, groundwater, and how all that affects the surface and subsurface. And then finally, resources and energy resources. So in this lesson, we're going to be looking at three main things. One, how is matter organized? How is the solid portions of the earth organized, going from atoms into rocks? Two, we'll look at the formal definition of a mineral. It's a very strict definition. What it is to be a mineral has five main parts, and we'll discuss those. Some of these you already know. And then the last thing we'll do is look at some very basic minerals and their properties and how to identify them. So first off, the organization of matter in the universe, of course, atoms to elements to compounds. When we get to the earth structure and composition, we then move into minerals, and then minerals make rocks. I always think of it kind of like Legos and how things are put together and how different Legos can come together to make all kinds of structures and different things. So matter is organized in much the same way. So where do we find minerals? Well, the easy answer is everywhere. Minerals are everywhere, whether you realize it or not, from deodorants, interesting, toothpaste, glass, cleaners, lipstick, makeup, your plumbing, even in rugs and your flower pots, all kinds of things found in the bathroom. In the kitchen, there's metals, which are derived from minerals. All those appliances, all those electronics, they all contain minerals. And of course, your table salt, which a lot of you probably already knew, that's a naturally occurring mineral. It's sodium chloride. That is a mineral. The computer that you're using, or your Chromebook, the chair, the point is, I think you get it. Minerals are everywhere. We use minerals constantly in our everyday lives. Without it, our modern civilization just wouldn't be possible. Sorry about that. All right. Oh, the brick in your house, the tiles on your roof, all of those are also made of different minerals. So in class, we kind of did this activity, but let's just review. What are the most abundant elements in the universe, the atmosphere, biosphere, hydrosphere, geosphere? So we'll start with the big one, the universe. It's hydrogen and helium. That is the primary elements of stars. And of course, stars make up most of the solid matter of the universe that we can see. There's also this exotic matter out there called dark matter, but in the universe, it's hydrogen and helium. In the atmosphere, nitrogen and oxygen. Most of you knew that one as well. Nitrogen, 78% of the atmosphere, oxygen, 21%, and that 1% that's left over is everything else: carbon dioxide, water vapor, argon, and other gases. How about the biosphere? The biosphere is an interesting one. As I think I've said before in class, all living things are based on the element carbon. That is the number one. Number two is oxygen. In the hydrosphere, you probably guessed this one as well, H2O, hydrosphere, hydrogen and oxygen. But the geosphere is kind of a surprising one. So the most abundant elements in the geosphere, in the crust, where we live, the portion of the earth that we are standing on now, is actually silicon and oxygen. Oxygen being the number one, silicon being number two, and then there's aluminum, iron. A lot of people guess iron, but it's actually not very prevalent in the Earth's crust. As you get further down, of course, that number will increase. And you can see the proportions of other elements there. Turns out oxygen and silicon combine to make one of the most common minerals on Earth in lots of various forms. Just call it silica, but quartz, amethyst, those are all variations of silica. So what is a mineral? What does it mean to be a mineral? What is the formal definition of a mineral? 5 main parts. Please make sure you remember these. A mineral is a naturally occurring inorganic solid with definite chemical composition, crystalline structure, and unique physical properties. Again, please commit those to memory. Some people will think of it as 6. I always think of it as 5, inorganic solid as 1, but naturally occurring inorganic solid with definite chemical composition, crystalline structure, and unique physical properties. We're going to look at each one in turn. So if a mineral has to fit that definition, what then is a rock? Well, a rock is an aggregate of minerals. All minerals in pure form we can consider a rock, but a rock is a combination of different minerals. For example, granite. Granite's a combination of different minerals, primarily quartz, feldspar, and a darker mineral called hornblende. Those can occur in different ratios, and so we just have to look at the ratio of each mineral that's occurring in that rock. So let's break it down. Naturally occurring. Naturally occurring means it cannot be created artificially. It has to be created in nature. So some examples, non-examples, would be glass, steel, concrete. All of those are solid and they're inorganic, but they are man-made, so they're not naturally occurring. Inorganic means it cannot be formed from a living thing or contain organic materials. Some non-examples, shells, wood, coal. They're all naturally occurring, they're all solid, but they are not, but they are organic. So a mineral has to be inorganic. Definite chemical composition. So each mineral has a unique, consistent chemical formula. Some examples down there at the bottom: gold, it's just gold. Au, gold. Quartz is it's another mineral, very common, like I said, the most common mineral on the surface of the Earth, silicon and oxygen. Orthoclase gets a little bit more complicated, and some minerals are very complicated as far as their chemical structure, but orthoclase contains potassium, aluminum, silicon, and oxygen as well. So rocks are aggregates of minerals with variable ratios. So rocks don't tend to have that consistent chemical formula. All minerals have, say all, there's always exceptions, right? Almost all minerals have an ordered arrangement of atoms. So it's a repeating geometric pattern from that chemical compound that just multiplies over and over again. For example, another non-example, glass. Glass is solid, it's inorganic, it can be naturally occurring. However, glass does not have that ordered arrangement of atoms. It's much more amorphous. Of course, liquids and gases cannot be considered a mineral because they're not solid, and they definitely don't have that crystalline structure. Over here on the right, you'll see lots of different types of crystalline structure. Each mineral, we can classify them and organize them into different crystalline shapes. And down here at the bottom, you'll see some examples. I'll show you one. This is the mineral pyrite, also known as fool's gold. We have lots of samples of this in the class, but I'm going to show you that crystalline structure and what I mean. So you'll see pyrite is basically a cube. And how that works is pyrite is a combination of just 2 elements, iron and sulfur. So that iron and sulfur repeats itself in a geometric pattern over and over and over again. So I can zoom out and make it a little bigger. Here we go. You can see that it's a cube as well. And over again. Just 2 atoms, and it's just how they combine. And that crystalline pattern is just repeated over and over and over again. All right. Oops. Next, all minerals have unique physical properties, a combination of unique physical properties. These are the properties that we use to identify them. Properties such as color, streak, hardness, luster, how it breaks, cleavage versus fracture, that crystalline structure as well. Density, very nice property that we can use to classify mineral. And then any special properties, like some minerals are magnetic, some minerals are radioactive, some glow under ultraviolet light, some have a special taste, like halide or salt. So, special note on density. Density is a formula. Of course, you know this is a property of minerals that we can use to identify it, but density is equal to mass divided by volume. How much matter in how much space. If you are interested, please go back into the presentation. You can watch the video there about Archimedes and a king's request to see if a crown was pure gold or not, if he'd been cheated by a goldsmith. But density is an excellent identifier of a mineral. For example, fool's gold, pyrite, we just looked at, versus real gold. Real gold is extremely dense, extremely dense. All those movies that you see where people are carrying around huge duffel bags full of gold bricks, nah, good luck picking up two. So gold is very, very dense. Pyrite is dense, but nowhere near as dense as gold. Color. Now, lots of minerals have beautiful colors, but color is not really a good indicator for a mineral because there are very similar colored minerals out there. Many different minerals can have very similar colors, and the same mineral can be different colors. It just depends on inclusions of different elements inside of that chemical matrix. For example, there are 4 minerals here. They all look very similar. They all are clear. One of these is worth a lot of money. The rest, not so much. You know which one? Yep, it's this one. It's the one over on the far left. That is diamond. The next one is quartz. Then we have some calcite and then some halite. All of those, the last 3 there, you can find in any gem shop. I have some samples that we'll be looking at, but not diamond. Diamond, even though it has that same color, it's very different. You can look at the crystalline matrix on all of these, that geometric pattern. That's a good indicator. That along with other materials or other properties. Sorry, that's selenite. My apologies. So another identifier is streak. Streak is a test that we can perform on minerals to help identify them. Streak is the color of the powdered mineral on an unglazed tile. It's called a streak plate. So very similar colored minerals can have different colored streaks. It's that powder that's left behind. Sometimes, for example, we have these 3 minerals here. One is hematite, one is limonite, and one is sulfur. Even though the 2 kind of reddish, ruddy colored ones look pretty similar, their streaks are very different. Again, when you have time, come back and watch the video on mineral identification. We'll be doing this a lot in class as well. Streak test for gold versus pyrite is also very different. We've kind of already talked about that, but gold, not is density, of course, is a great indicator, but streak can also help you as well. Whereas gold has a kind of a yellowish streak, pyrite has more of a gold or brown streak, and maybe even a greenish color in there as well. The next property I want to talk about is something called Mohs hardness scale. So it's a measure of the ability of a mineral to scratch different things. It's an easy scale. It goes from 10 being the hardest, example, diamond, 1 being the softest, for example, talc. If you look at this diagram here, as we start at the bottom, talc, 1, gypsum, 2, your fingernail has a hardness of about 2.5. So if your fingernail can scratch it, it's got to be below 2.5. As we move up, copper, a penny, has about a 3.5 rating on the Mohs hardness scale. Of course, your finger can't scratch copper penny, but anything above 3.5 is able to. So fluorite, apatite, orthoclase. Glass plates are about a 5 to a 6. So if the mineral can scratch the glass, then it has to be above that. If it cannot, it's got to be below. So using the Mohs hardness scale, one mineral scratching another, or scratching these very common items from steel all the way down to your fingernail, is also another good indicator of the mineral, helps you identify it. So in the notes, there is a mineral logic puzzle for you to try. I'd love for you to go through that. It's actually pretty simple. Use the clues, identify the name of the mineral based on its ability to scratch something else. If you want the answers to the puzzle, it'll be at the end of the presentation. All right, moving on to luster. Luster is how a mineral reflects light, or how light bounces off its surface. And we divide that property into two basic ones. There's metallic luster, it looks like metal, and then a non-metallic luster. And you can get into much more specific types of luster, but for our purposes, we'll just go metallic, non-metallic. Cleavage versus fracture. Okay, so cleavage is the tendency of a mineral to break along smooth planes. Some mineral may break only along one plane. Some really cool ones break along all planes, all three. So for example, in this video, we have calcite. When it breaks, it just breaks into more kind of rhombus shape. You take a smaller one, you break it, it breaks into even smaller. So you can see all the bits and pieces there. They're all the same basic geometric pattern, and just get smaller. So we refer to calcite having perfect cleavage. Halite or table salt as well. It's a cubic structure. So when it breaks, it just breaks down into smaller cubes. If you've ever looked at your table salt with a magnifying glass or a microscope, you'll see that cube shape. Oops. Now, fracture is the opposite of that. Fracture is the tendency of a mineral to break unevenly. For example, quartz, again, that most common mineral on the face of the planet. So when quartz breaks, it just shatters. It doesn't really break along the nice planes like calcite and halite. So we refer to that breaking into just irregular shapes, fracture, and if it breaks along nice smooth lines, cleavage. Going back to crystalline structure, again, the arrangement of those atoms can help us identify them. And those crystalline structures actually form due to the conditions under which the mineral forms, and it has to do with heat, pressure, the presence of water as well. A lot of minerals are hydrated or have water in their chemical matrix. So all of those things affect how those crystals forms. In general, if a mineral forms extremely slowly, it gives those atoms, those molecules, those compounds more time to align, and you'll have a nice crystalline structure. If they form very rapidly, you tend to have much more jumbled shapes. For example, this is an excellent video. I highly advise going back in and watching this. This is on the, it's called the Nica silver mine. It was a cave in Mexico, a silver mine that was, they go down, I think, I can't remember exactly how far, a mile or two. So anyway, they ran into a big pocket of water. They pumped out all the water, and it's extremely hot. There's a magma chamber very close by, extremely hot down there. So they pumped out all the water. They're looking for silver. They go into a new opening, and I mean, you can see the picture here. That's what they found. Those are huge, huge, huge crystals of selenite. If you're familiar with Superman's Fortress of Solitude, that's the natural example. These are not very expensive minerals. These are very common minerals, but it was the conditions under which it formed. These minerals formed from high heat, long time with minerals dissolved in the water, and it allowed those crystalline shapes to form. So as soon as they pumped out the water, the minerals will stop growing and actually become soft over time. The cool thing about this place, though, of course, is that the water, if there was any life in it or any evidence of life that could be trapped in those crystals. And so scientists are allowed to go and explore and take samples and things like that. Here's the trick, though. It's 100% humidity and the temperature is over 120 degrees Fahrenheit. Under those conditions, you sweat, but your body does not cool off and you rapidly go into organ failure. So if you look very closely, you'll see the scientists there, but they're wearing backpacks with dry ice and they pull air through the dry ice to cool inside their lungs and to keep their bodies cool. But even with all that equipment, they still only can stay down, I think, about 30 minutes. Anyway, great video to watch. Please take some time to look at that. There are some other properties that we use to identify minerals as well. Some of those special properties like density, mass divided by volume. Is it magnetic? Does it have a smell? For example, sulfur, excellent mineral, horrible smell. If you've ever lit a match, that's a lot of that smell that you get is sulfur. There's fluorescence. Fluorescence is a property of a mineral where it glows under ultraviolet light. There's phosphorescence, where it glows of its own accord after that ultraviolet light has been removed. Think of it as glow in the dark. And then there's something called chatoyancy. It's that cat's eye effect, how light plays inside of the mineral and is bounced off and reflected. So again, fluorescence is it glows under UV, and then phosphorescence means it continues to glow after the UV light has been pulled away. In this image, you can see there's been a black light or a UV light over the minerals, and we'll do this in class as well. And you can see how they glow. This is chatoyancy, the cat's eye effect. And you can see tiger eyes have that effect. You'll see that a lot. This is an interesting one. This one is called iridescence. Iridescence is the rainbowy effect. I have a sample in the back of the class of bismuth. And that's what you see here on the right-hand side. That's iridescence. All right, we are going to start classifying minerals and get into a little bit more detail in a later class, because that will allow us to move into mineral uses, because the usage of a mineral is really based on its chemistry, and we can divide minerals up based on that chemistry. But for now, we're only going to break minerals down into two main groups. There are the silicates and the non-silicates. That's all the others. And the non-silicates contain things like carbonates and oxides, pure minerals like gold or even iron can be found in pretty pure form. There's sulfates and other types, but for now we're just going to divide it into silicates and non-silicates. The silicates is by far the largest group. Again, quartz and those silicates are the most common minerals on the surface of the earth. Real quick, ores versus gems. So you may have learned this in a previous grade. What is an ore? What is a gem? So an ore is a mineral that contains something useful, something that we can mine, something that we can sell for profit. And most are non-silicates. Some are silicates, and they are the primary source of metal. So hematite, for example, is a type of iron ore. We can extract iron from that. Galena is a type of metallic mineral that contains sulfur and lead. We can actually extract the lead from that. Malachite, another one, contains copper. So all those are ores. They have to be extracted profitably in order to be useful and to be considered an ore. A gem, on the other hand, is a mineral that is prized because they're pretty. We can cut and polish them and make light sparkle inside of them and reflect out. Most of the times they're pretty hard. They're pretty high up on the Mohs hardness scale. For example, diamond, which is a 10. Emeralds, rubies, and sapphires are all 9s on Mohs hardness scale. Actually, corundum, I believe, is the mineral that those come from. So gems really are just pretty. We can cut them, polish them, make them look spectacular and shine and sparkle. All right, that comes to the end of our first little bit of exploration into minerals. Again, we're going to be looking at tons of examples in class. You're going to be looking at properties of different minerals, identifying them by sight and by those properties. I really enjoy minerals. I think it's fascinating. If you're into chemistry, I think that you will make a logical jump into minerals because of how ordered and regular they are. They're quite beautiful in all their different forms. Here's the answer to the logic puzzle. If you have any questions, please let me know, and look forward to working our way through Earth's materials and into rocks next. Thank you.